Today's assignment deals with completing the square and the quadratic formula. So if I had x squared minus 6x minus 16, I can factor that into what? X minus 8 and x plus 2. Okay? And then the roots of that would be 8 and negative 2. Okay? But what if I was dealing with x squared minus 6x? Oh, that was minus 16. Let's do minus 14. Are there two numbers that multiply to be 14 and add to be negative 6? No, my only choices are 1 and 14 and 2 and 7. And there's no way to make a negative 6 out of any of those. So, does that mean that this quadratic misses the x-axis? Maybe, right? What it does tell me is it does not hit the x-axis at any friendly number, like a whole number or a fraction. Okay? If the roots are fractions or integers, then it is factorable. If it's not factorable, then one of two things happens. Either the roots are not real, or they are irrational numbers. Okay? And that one, in fact, is going to be two irrational numbers. And I know that because the y-intercept is negative 14. So it would have to hit the x-axis. So what do we do? Well, there is this interesting little type of quadratics that we deal with. So if I had x squared, let's do plus 8x and plus 16. How does that factor? X plus 4 and x plus 4. So I could condense those into x plus 4 squared. This is called a perfect square trinomial, and you don't really need to remember that, but it's a quadratic that was created by duplicate factors, which means it was created by duplicate roots. And by the way, what do duplicate roots look like on the x-axis? So the roots here are negative 4 and negative 4. It's a bounce, right? The quadratic comes down, bounces off the x-axis, and goes back up. And you can see that. Let's see if it will let me move this. So that parabola has two roots, two roots, two roots, two. Now it has one duplicate root. What happens if I go further up? Now the roots are imaginary. They still exist, but they're complex numbers. Okay? So this number here kind of determines whether or not the graph is going to hit the x-axis. If that number is big enough, then the graph will miss the x-axis. And you see that according to where this graph touches the y-axis. Okay? So, okay. What about x minus 6, x squared minus 6x plus 9? That would factor into x minus 3 and x minus 3. Okay? X squared plus 10x plus 25. That would be x plus 5 and x plus 5. Do you see any patterns here? What qualities do each of those quadratics have? What is similar between all three of those quadratics? They all have a positive constant. Why is that? Good. So this number has to be positive. Because anytime you have a duplicate root, you're either multiplying two positives or two negatives. Good. What else do you notice? What do all of the constants also have in common? They're all a specific type of number. They're all perfect squares. 16, 9, and 25 are all perfect squares. Okay, now for the harder question, what do these numbers have in common? The sign matches the factors. What else? What's half? Okay, and we're actually going to go backwards, but you're right. The middle coefficient is twice as big as the factor, and it shares the same sign. Okay, now if we rely on that, we can do something really cool. So let's say I had x squared plus 8x plus 14. Let's not do 14. Let's do minus 8x plus 18. Okay. Are there factors of 18 that add to be negative 8? No, there are not. Ooh. Whatever. I'm just going to run with it. So, what if I had this? That is something special. What is it? That is a perfect square trinomial. And I know that that factors into x minus 4 squared. Well, if I know that, let's make this a minus 4, just for fun. So if I add that 4 to the other side, now I could take the square root and solve it just like we did yesterday. Does that make sense? So sometimes quadratics will not factor, but we can force them to factor using this idea of perfect squares. So let's go back here. Okay. So I'm going to solve both of these using the complete the square method. So this number is not the number I need for my perfect square, right? So I'm going to move that number to the other side of the equal sign. And I get x squared minus 6x, I'm going to leave a space, is equal to 16. Okay? What number should go here to create a perfect square? How did you get 9? Half of negative 6 is negative 3, and then square it, and I get plus 9. Okay? Well, now that this is a perfect square, how does it factor? X minus 3 times x minus 3, but we're lazy, so we're just going to do this. And now what does that equal? Not 16. Yeah, I broke the rule. I decided to add 9 pounds to the left side of that equation, which is okay as long as you do the same thing on the other side. So I need to add the equal amount to the other side, and I get 25. Yeah, that's nice. Now I take the square root, and I get x minus 3 is equal to plus or minus 5. And now I add 3 to that, and I get x equals 8, and it's 8 and 2. Negative 2. Okay. Why did I bother? Isn't that what I got when I factored it? Yes, but completing the square will always work. Factoring only works if the answers are rational. If the answers are imaginary or irrational, factoring will not work. So let's try this on an equation that you cannot factor. We don't know what this answer is at the moment. I'm going to move the 14 to the other side. Okay, so half of that will be negative 3. And then I square it. Oh, that's not going to be very nice. Whatever. We follow? Now I take the square root, and I get x minus 3 equals plus or minus the square root of 23. Does the square root of 23 simplify? No, it's prime. Okay. Now, just for argument's sake, let's say it was a 24. How does 24 simplify? Well, here's a fast way to do it. Are there any perfect squares inside 24? 4. And what's the square root of 4? 2. And if I bring a 4 out, what's left in? 6. So 2 root 6 should be my answer. Now, if you don't know how to do that, you take 24, 4 and 6, 2 and 2, 2 and 3. How do I bring stuff out? I pick pairs. For every pair, I bring one out. So I bring out a 2, and I have a 6 left over. And all you're really doing is square rooting the perfect squares. So 24 is not a perfect square, but one of its factors is a perfect square. So we square root that piece of it, and then we just leave the rest behind. Okay, and then I add 3, and that would be my answer. 3 plus or minus 2 root 6. Okay, we get that? Notice it worked, and there was no way to factor and get that answer. Okay, let's do another one. Let me see here. Let's do so to complete the square, I move the 40 to the other side. Okay. And then this becomes x minus 6 squared. So I need to add 36 here. And if I add 36 to one side, I have to add it to the other side. And I get negative 4. Am I going too fast? We're good? Take the square root. X minus 6 is equal to plus or minus 2i. And then I bring the 6 over. And I get 6 plus or minus 2i. What if it would have been 6 plus or minus the square root of negative 5? I put the I, and where do I put it? I's go behind numbers, behind variables, but in front of square roots. So that I will be put right there. We change the 5 to positive, and we bring the I out. So for an I, if I had 2xy squared I root 3, that is where i's belong, between the variables and the square roots. Okay, does that make sense? All right, let's do a harder one. Why is that going to be harder? It's a 5. What's wrong with the 5? It doesn't cut in half very nicely. So, x squared minus 5x, leave a space, equals negative 2. And here's the trick. Stick with fractions. don't do decimals. You can do decimals on your calculator, but fractions you can do much faster on paper. So, what goes in here? And actually, let's do one that works. Let's say -6. And then we'll do one that's a little bit harder in a second. So half of -5. So I'm just going to write -5 halves. And the reason I do that is multiplying fractions is way easier than multiplying decimals. What is -5 halves times -5 halves? It's just 25 over 4. So this is 25 over 4. Well, how many fourths are there in 6? 24. And what is 24 over 4 and 25 over 4 added together? 49 over 4. Oh, I like that. Why do I like it? They're both perfect squares. Take the square root, and I square root the top, and I square root the bottom. X minus 5 over 2 is equal to plus or minus 7 halves. Sure. Okay, now I add 5 halves. And notice they have the same denominator, which will always happen if it simplifies. 5 times 7 is 12, and 12 divided by 2 is 6. And 5 minus 7 is -2, divided by 2 is -1. Man, that was handy. Okay, let's do the same thing, but let's make it not so nice. So let's say this is a -8. So I add 25 over 4. And you could, I don't care if you use your calculator on this, except my calculator on the other screen. So, -8 minus 25 over 4. And I end up with -57 fourths. Okay, I take the square root of both sides, and I get x minus 5 over 2 is I root 57 over 2. And then when I add that 5 over 2 to the other side, they have the same denominator. So I can just put them all over the same 2. Okay, does that make sense? Let's see. Oh, we got all sorts of time. We're good. Okay. Look at number 46. You do not want to solve a quadratic that has fractions in it. How would you fix 46 so it didn't have fractions? Multiply the whole thing by 6. Will that change the graph? Yes. But it won't change the roots. Okay? So 45 you're going to multiply by 4. What happens if we have a leading coefficient? So let's say 2x squared minus 8x plus 10. Okay? Completing the square only works when your leading coefficient is a 1. Okay? So, we have to make it a 1. Now, this is going to be kind of complicated, so pay attention, ask questions if you get confused. First off, I got to get the 10 out of the way. So 2x squared minus 8x, leave a space, equals -10. All right? Now, I've got to get this 2 away from the x squared, or completing the square doesn't work. Now, that's not totally true. I could force it to work, but it's too complicated. So to make my life easier, I'm going to pull out a 2. But if I do that, I also have to pull a 2 out of here. And then I get x squared minus 4x equals negative 10. Does everybody follow? Okay. Now, this is going to be x minus what squared? 2. So what should I put here? Positive 4. What should I put on the other side? Do you guys see that? I did not add 4 pounds to the left side. I added 4 pounds to the inside of that set of parentheses. But that is hiding underneath the 2. So by placing a 4 here, I'm actually placing an 8 there. Which means I need to do 8 on the other side. And then this would be negative 2. And then I would divide by 2, get negative 1. I would take the square root and get plus or minus I, and I would add 2, and I get 2 plus or minus I. Okay, that was super fast, but do you guys understand the leading coefficient problem? Now, it can get really complicated, because if you had something like negative 3 x squared minus 7x equals whatever, 5, we have 2 problems here. I've got to yank out a negative 3, which makes this nasty. And then I have to divide the 7/3 by 2. Oops, sorry. And then what would go here? 49 over 36. And then what would go here? Well, this number is going to be negative 3 times that. And so I need to do the same thing over here. So minus 3 times 49 over 36. What a mess. We don't want to do that. So we realized long time ago that completing the square can get really complicated. In fact, if there's a leading coefficient, I don't ever complete the square. Unless I have to. Sometimes you need the perfect square to figure it out. Okay? So we've invented a formula. And some really smart people put the formula together. And you know what the formula is, but you probably don't know where it came from. I want to know... That was bad. I want to know what are the solutions to that equation. That represents every possible quadratic in existence, right? So if I complete the square on this, then I will get a formula that I can plug numbers into and solve quadratics without completing the square. So what you do, you move the c out of the way. Okay, and then you pull out the a. And how do you pull an a out of that? It's weird. And then you finish all the math, and it's kind of complicated. And when you get done, you're left with so that formula contains all of the steps of completing the square for every possible quadratic in existence. It's pretty nifty, right? So instead of completing the square on every quadratic, we completed the square on a generic equation and built a formula that will complete the square for us. So when you're completing the square, you are essentially doing all of this work one problem at a time. The quadratic formula does the work first, and then you just plug numbers in to solve. So if I had something like that terrible, I don't remember what I called it, but now I can just plug those numbers into the quadratic formula. So the opposite of b is 7 plus or minus the square root of, and I recommend you do it this way, 7 times 7 is 49, and then negative 4 times 3 times 5 is negative 60 over 6. Okay, so 7 plus or minus the square root of negative 11 over 6, which gives me 7 plus or minus I root 11 over 6. All right, in your assignment today it says, solve by completing the square, solve using the quadratic formula, and solve using any method. I don't care how you solve them. I would never complete the square if there's a leading coefficient. It's just not worth it. And then make sure that you do complete the square on some of them, but if you prefer the quadratic formula, then use the quadratic formula. Okay? And then problems like 57, make it easier by multiplying everything by 4, or no, 12, to get rid of the fractions. Okay? What if we did every other odd? Yeah, so do 35, skip 37, do 39, skip 41. Does that sound fair? Okay. Every other odd. Get to work.